In the next exercises, we're asked to prove an algebraic identity. To start, we're going to write that the left side of the equation is equal to itself. And remember, the thing that we're trying to prove is written above, so what we're going to do is we're going to try to transform the right side of the equation into 4 times a plus 2. So I'm going to leave the left side of the equation as is, and then perform some operations to simplify that left side of the equation, the right side of the equation, first of which can be distributive property. So if we distribute the multiplication by -2, we get -6 plus 4a. I'm going to leave the left side of the equation alone and then combine some like terms. And then on the right side, I'm going to reuse the distributive property, but this time I'm going to undistribute or factor. So I'm going to factor out a 4, and that will leave us with 2 plus a. And that's very nearly what is written on the right side of what we're trying to prove. So the next thing I'm going to do is just change the order of the addition, which is allowed by the commutative property. And once we get to that last step, we've proven what we were trying to prove. All right, in number 10, a similar statement, 2 over 5x plus 3 over x squared is equal to 2x plus 15 over 5x squared. But I'm going to start by establishing that the left side of the equation is equal to itself. I'm going to leave the left side of the equation alone, and then transform that right side. So if we want to add two fractions, we need a common denominator. So I'm going to multiply the first fraction by x over x, and then multiply the second fraction by 5 over 5, and that will give us 2x over 5x squared plus 15 over 5x squared. Again, leaving the left side of the equation alone. And then on the right side, once we have two fractions being added with the same denominator, we can just add the numerators and keep the denominator. And now we have the statement that we were trying to prove, so we are done. Trigonometric identities can be proved the same way as the algebraic ones. So I'm going to start with tangent of theta times the cosine of theta is equal to tangent of theta times the cosine of theta. Now our job is going to be to transform that right side of the equation into sine of theta. So a good strategy is to re-express any trig functions in terms of sine and cosine. So tangent of theta can be re-expressed as sine of theta divided by cosine of theta. And cosine of theta can be written as cosine of theta divided by 1. Now I can cancel common factors, and the right side of the equation will turn into sine of theta, and I'm just going to leave that left side. And now we have the statement that we're trying to prove. So I'm done. QED stands for quod erat demonstratum in Latin, means basically I've shown you what needed to be proven, and you can write that or not. That's a stylistic choice on your part. In number 12, we have another trig identity to prove. So I'm going to start with the cosecant of theta times the tangent of theta is equal to the cosecant of theta times the tangent of theta. And then our job is going to be to transform that right side. So I'm going to leave the left side alone. And on the right side, I'm going to re-express in terms of sines and cosines. Cosecant of theta is 1 over the sine of theta, and tangent of theta is sine of theta over cosine of theta. Now I can cancel common factors of sine in that multiplication, and then that will leave us with 1 over the cosine of theta on the right side, and bringing down cosecant of theta times the tangent of theta on the left. We have one thing left to do, and that's to re-express 1 over the cosine theta as secant of theta. Now we've proven what we needed to, and we're done with the proof. In number 13, I'm going to start with the left side of the equation equal to itself. And it will help if I write it correctly. That was the cotangent of theta times the cosine of theta times the sine of theta is equal to the cotangent of theta times the cosine of theta times the sine of theta. And we're going to leave the left side of the equation alone as we proceed to subsequent steps, and then re-express the left side. So cotangent of theta can be rewritten as cosine of theta divided by the sine of theta. Cosine of theta can be written as cosine of theta over 1, and sine of theta is just sine of theta over 1. Now I can cancel some common factors of sine of theta in that multiplication on the right, and that leaves us with cotangent of theta times the cosine of theta times the sine of theta is equal to cosine of theta times cosine of theta, which is cosine squared of theta. Now we've proven what we needed to, and we're done. In number 14, I'm going to start with the cosine of theta divided by the cotangent of theta is equal to the cosine of theta divided by the cotangent of theta. We're going to leave the left side of the equation alone. And on the right, we can rewrite this using a different division symbol for convenience. And that will be the cosine of theta divided by 1 times the reciprocal. And so when we do a division of fractions, we multiply by the reciprocal, and the reciprocal is tangent, and tangent is sine over cosine. And now we can cancel our common factors of cosine, and we have cosine of theta divided by cotangent of theta is equal to the sine of theta. Now we've proven what we need to, and we're done with that proof. In number 15, we have cotangent of theta divided by cosecant of theta is equal to cosine of theta. So cotangent of theta divided by the cosecant of theta is equal to cotangent of theta divided by the cosecant of theta. In my next step, I'm going to leave that left side of the equation alone. Cotangent of theta divided by the cosecant of theta is equal to, and I'm going to rewrite using a division, but at the same time, I'm going to do some re-expression here. The cotangent of theta is equal to the cosine of theta over the sine of theta, and we are dividing by the cosecant of theta, which is re-expressed 1 over the sine of theta. Leave the left side alone, and we can invert and multiply, and then cancel our common factors of sine, and now we have the cotangent of theta divided by the cosecant of theta is equal to the cosine of theta. And now that we've proven what we need to, we are done with that proof. In number 16, I'm going to start with the sine of theta plus the cosine of theta squared is equal to the sine of theta plus the cosine of theta squared. Now I'm going to leave the left side of the equation alone and transform the right. Sine of theta plus the cosine of theta squared is the same as sine of theta plus cosine of theta times sine of theta plus the cosine of theta. Leaving the left side alone, we can go ahead and multiply by the FOIL method, if you wish, the right side, and that will give us a first term of sine of theta times sine of theta, which is sine squared of theta. And then the product of the outers and the inners are both sine of theta times cosine of theta. So if we add those two together, we get 2 times the sine of theta times the cosine of theta. And now the product of the last terms is cosine theta times cosine theta, which is cosine squared of theta. And now we're going to leave that left side alone. Sine of theta plus the cosine of theta squared is equal to, and I'm going to change the order of the terms on the right side to sine squared of theta plus cosine squared of theta plus 2 times the sine of theta times the cosine of theta. And I did that because, looking at our target, 2 times the sine of theta times the cosine of theta is by itself as a last term. Now we have one more thing to do on the right side of the equation, and that is sine squared of theta plus the cosine squared of theta is equal to 1 because of the Pythagorean identity. So that can be replaced, and now we've proven what we need to, so we are done with this one. In number 17, we have 1 plus the cosine of theta times 1 minus the cosine of theta, and we're trying to prove that that's equal to 1 over cosecant squared of theta. So I'm going to start with a statement that 1 plus the cosine of theta times 1 minus the cosine of theta is equal to itself. Now we're going to leave the left side of this equation alone in subsequent steps and transform the right. And since we have 2 parentheses being multiplied or 2 binomials being multiplied, I can use the FOIL method to multiply. And the product of the first is 1. The product of the inners is positive cosine of theta. Product of the outers is negative cosine of theta. Those add up to 0. And the product of the lasts is negative cosine squared of theta. Again, leaving the left side alone, we're going to transform the right, and 1 minus cosine squared of theta is a variation of the Pythagorean identity. Remember that sine squared of theta plus the cosine squared of theta is equal to 1. So if we subtract cosine squared of theta from both sides, 1 minus cosine squared theta is equal to sine squared of theta. Now, leaving the left side of the equation alone, we have sine squared of theta, and remember sine is the reciprocal of secant, so sine squared of theta must be equal to 1 over the cosecant squared of theta. Now we've proven what we need to, so we are done with that one. In number 18, we have an equation with natural log. Now, in order to perform this one, we're going to need to remember a natural log identity, and that natural log identity is natural log of A minus the natural log of B is the same as the natural log of A divided by B. So we start with the natural log of the cosine of theta minus the natural log of the sine of theta is equal to itself. We're going to leave the left side of this equation alone. So the left side will remain natural log of cosine of theta minus the natural log of sine of theta, but we can use that natural log property on the right side. So the right side can be transformed into the natural log of the cosine of theta divided by the sine of theta. And again, we're going to leave the left side alone. And on the right side, the cosine of theta divided by the sine of theta can be re-expressed as cotangent of theta. Now we've proven what we needed to, and we are done with this one. In number 19, we're going to start with the cosine squared of theta minus the sine squared of theta times the cosine squared of theta is equal to the cosine squared of theta minus the sine squared of theta times the cosine squared of theta, or the left side equal to itself by the reflexive property. Now I'm going to just recopy what is on the left side, and then I'm going to factor on the right. I'm going to pull out a common factor of cosine squared of theta, and that will leave us with 1 minus the sine squared of theta. In our next step, I'm going to leave the left side of the equation alone. And on the right side, I'm going to use the Pythagorean identity to replace 1 minus sine squared of theta with cosine squared of theta. And on the right, cosine squared of theta times cosine squared of theta is the cosine to the 4th power of theta. And now we've proven what we need to and are done with this one. In number 20, we can start with secant of theta minus the cosine of theta is equal to secant of theta minus the cosine of theta. I'm going to leave the left side of the equation alone, and on the right side we have a subtraction. Now we can't perform a subtraction unless we have fractions that have common denominators. We do know that secant of theta is 1 over the cosine of theta, so that is a fraction. And then I'm going to subtract cosine of theta over 1. And if we want a common denominator to be able to subtract those, I'm going to multiply that second fraction by cosine of theta over cosine of theta. So that's going to give us secant of theta minus the cosine of theta is equal to 1 over the cosine of theta minus cosine squared of theta over cosine of theta. From this point, we have secant of theta minus the cosine of theta is equal to 1 over, or rather, now that we have common denominators, we can subtract those fractions, subtract the numerators, and keep the denominator. And now, using a Pythagorean identity, 1 minus cosine squared of theta is one of those variations on the Pythagorean identity. So 1 minus cosine squared of theta is equal to the sine squared of theta. And if you remember, that's what we were trying to prove. So now we've reached the desired last step and are done with that proof. In number 21, I'm going to start by writing that the sine of theta times the tangent of theta plus the cosine of theta is equal to the sine of theta times the tangent of theta plus the cosine of theta, which could be justified by the reflexive property. Now we're going to leave that left side of the equation alone, and we're going to write the right side of the equation. We're going to do some rewriting on that right side of the equation. And for this one, I guess we're going to need to re-express tangent of theta. So sine of theta divided by 1, that's sine of theta, and tangent of theta is sine of theta divided by the cosine of theta. And then cosine of theta can be re-expressed as cosine of theta over 1. Leave the left side alone, and on the right side, If we multiply the fractions, we have sine squared of theta divided by the cosine of theta. Now, if we're going to add that second fraction to it, we're going to need a common denominator. So I'm going to multiply by cosine of theta over cosine of theta to get a common denominator. And that will give us cosine squared of theta divided by cosine of theta. I'm going to leave the left side of this equation alone. And then on the right side, since we have fractions with a common denominator, we can simply add the numerators and keep the denominator. Leave that left side of the equation alone. And on the right side, sine squared of theta plus cosine squared of theta is equal to 1 by the Pythagorean identity. And now we have one thing left to do. Leave that left side of the equation alone. Sine of theta times the tangent of theta plus cosine of theta is equal to 1 over the cosine of theta, which can be re-expressed as secant of theta, since secant of theta is the reciprocal. We've now proven what we were aiming to do. So we're done with that proof.
No chance.
In number 22, we're going to start with the cosecant of theta minus the sine of theta is equal to the cosecant of theta minus the sine of theta. We're going to leave the left side of this equation alone and transform the right. Cosecant of theta is 1 over the sine of theta, and sine of theta is sine of theta over 1. If we are going to subtract these fractions, we'll need a common denominator, so we're going to multiply the second fraction by sine of theta over sine of theta. That will give us cosecant of theta minus the sine of theta is equal to 1 over the sine of theta minus sine squared of theta over sine of theta. Now that we have common denominators, we can subtract the numerators and keep that denominator. By the Pythagorean identity, 1 minus sine squared of theta is one of those variations on the Pythagorean identity and is equal to cosine squared of theta. Now let's remember what our target is. Our target is cosine of theta times the cotangent of theta. We're very nearly there. So I'm just going to recopy the left side of the equation. And on the right side of the equation, I'm just going to factor out that cosine of theta. So now we have cosine of theta over 1 times the cosine of theta over sine of theta. And the cosine of theta over 1 is the same as cosine of theta. And cosine of theta over sine of theta is the same as cotangent of theta. Now we've proven what we need to, so we are done with this one.